So how are we going to fit optimization in to our JavaScript interpreter? The basic plan is to change the parse tree before interpreting. That way we'll save time, especially if the optimization we made was in the inside recursive call of Fibonacci or factorial or something like that. So recall our general plan, the outline of our interpreter. We start with program text, which is a string, and we use lexical analysis to break it up into tokens or important words. This is implemented with regular expressions. Then we use parsing based on context-free grammars and dynamic programming to check and see if those tokens are in the right order. Are they valid syntactically? Do they form a sentence? If so, we end up with a parse tree, also called an abstract syntax tree. And now, here's the new part. We're going to do optimization, which will also yield a parse tree, but hopefully a simpler one. If all else fails, do no optimizations and return the same one. Then we do our interpreting, and that gives us the meaning of the program, the final result. So we're going to fit optimization in after parsing, but before interpreting. Optimization is always optional. You don't have to do it, typically, unless you're in some sort of company where timing really, really matters, like, say, a car's anti-lock brake system, where you might have to respond within a certain number of milliseconds. But for the vast majority of applications, optimization is optional, so often we do it last. In fact, let me show you a simple Python example of how a JavaScript optimizer might go. For now, I'll just optimize expression trees. We'll do these sort of arithmetic optimizations we've been thinking of. And for now, I'm going to focus on expressions that have expression type binop, binary operator. For example, maybe it's something like a times 1, and I just want to replace that with a. Well, here's a real simple way to do that. I'll just check and see if the operation is star, and I'll check and see if the right-hand side is literally the number 1. And if it is, then I can just return a. Otherwise, I'll return the original tree unchanged. Maybe it was something more complicated like 5 times 3 or 5 times x that we couldn't reason about. We could certainly put in more optimizations here, but now we have at least one. And the basic plan is right before we interpret an expression, we call optimize on it. Just to show this pictorially, let's say our input is 5 times 1. We're just going to replace that with 5. In our Python interpreter, that abstract syntax tree would show up as nested tuples. Binop involving multiplication. Oh, that's not exactly the order we use. There we go. A binop where the left child is 5, there's some multiplication, and then the right child is 1. And if these two parts match a pattern we've already established, then we'll just hoist this part out and return it unchanged. So we've gone from 5 times 1 to just 5 by looking at our Python abstract syntax tree, checking to make sure the optimization is legal. And optimization is only legal if it doesn't change the semantics of the program, doesn't change the meaning of the result. And then once it is legal, we just replace the tree with a simpler tree. The way I've written it, we're officially returning a new tree. Potentially, if we wanted to be a little more efficient, we could change it in place, but returning a new copy of the tree is fine for us.